Welcome to lesson number 8 on oscilloscope waveform math functions. In lesson number 7, we learned about active probes, and you saw a demonstration of using a high voltage differential active probe to measure AC line voltage and a current probe to measure input AC current of our function generator. Hi, I'm Johnny Hancock, product manager for Keysight Technologies Infinivision oscilloscopes. Now that we've been able to capture and display input voltage and current of our function generator, let's pick up where we left off in the last lesson and now measure the power consumption of this function generator. So here's our AC voltage input signal. It's measuring about 120 volts RMS, and the current, remember it's pulsed, it's measuring about 360 milliamps. Now you may be wondering about power, and you may have learned in your classes that power is voltage times current. But if you take the RMS voltage times the RMS current, that doesn't produce what's called real power. That's apparent power. And that would be about 43 volt amps, not watts. So what about real power? For real power, we need to multiply each waveform times each other, the instantaneous waveform. And we can do that with waveform math. So let's do that now. On this oscilloscope, there's a button on the front panel that says Math. It's located right here. On your scope, waveform math may be somewhere else. It may be buried in an analysis menu. But we just press Math, and then we can select what operator. So the default is add. The other selections are subtract, multiply, divide. There's a magnitude FFT, phase FFT, and a low-pass filter. Now, higher performance scopes have many more math functions, but this is probably enough for what you're doing in the university. So we need to select the multiply math function. Now it's multiplying channel 1 times channel 2 and producing this purple waveform. Now I'm going to rescale things so we can see it better. Now this scope has a dedicated knob for rescaling math. So I'm going to reduce that somewhat, position it down here in the center, and I'm going to move my current waveform up top here. Maybe reduce it a little bit so you can see it better. Now, what I want you to notice here is that when the voltage goes positive, the current has a positive peak. When the voltage goes negative, the current has a negative peak. But when we multiply the positive current times the positive voltage, we get a positive power. And when we multiply a negative current times a negative voltage, we get a positive power. It's always producing positive power pulses. What the power I'm measuring on this device right here is never delivering power, it's consuming power. So how much power is it consuming on average? For that, let's go into the measure menu and then change the source to math and select average in cycles. So it will measure the average power, and often the power just goes to nearly zero and then it's pulse. But the average power is about 14 watts. Remember I said the apparent power was about 43 volt amps. Now we're back to our resistive divider circuit, looking at the input signal across R1 and R2. That's the yellow waveform. It's measuring about 10 volts. And we're looking at the output across R2, and it's measuring 980 millivolts. That's about 1 volt. Both of these are pretty much what we expect. Now remember in earlier lessons when we talked about passive probes, I said we couldn't directly measure the voltage across R1. Now you can if you use a differential active probe, but we can determine the voltage drop across R1 using waveform math. Let's do that now. So I'll go into the math menu and select the subtract operator, and now we are subtracting the voltage from channel 2 from the voltage from channel 1, and the difference is the voltage drop across R1, and that's the purple waveform. So let's make a measurement on it. So I'll select measure. Let's change the source to math and add measurement, and it measures a little over 9 volts, which is pretty much what we expected. In our next lesson, we'll be talking about a special math function called FFT, or fast Fourier transform, which is used to convert a time domain waveform into a frequency domain waveform. Remember, for additional technical resources to help you learn more about oscilloscopes, go to the URL listed on your screen. See you in Lesson 9. Go Texas Southern University Tigers!